Okay, so doing these notes, you need to make sure that you have done the atom notes first. This is under the assumption that you understand what an atom is. So the periodic table is just a way that we've organized our elements. Dmitri Mendeleev was the person who created the organization system that we currently use today. There were many, many people before him that were doing this as well, but just didn't quite get there. His is based on increasing atomic mass and their physical properties, so things about them. This is an example of our periodic table. I want you guys to take note really quick of this zigzag line right here, because I'm going to mention that a couple of times, and also the fact that notice that hydrogen is the same color as these over here. Hydrogen actually doesn't fit with its column or any of the ones over here. He actually works well over here, but since he's over here because of his atomic mass. Okay, so I'm not going to, from here on out, I'm not going to refer to these as columns or rows. I'm going to call them by their proper names, which is if you're looking at a row horizontally, we're calling that, it is called a period. There are 7, and I will refer to them as such. The vertical columns are called groups. These are also called families. I'm kind of going to switch between that. I'm sorry. I'm used to calling them families, but they're also called groups, and so I will want you to know both of them. So these guys have similar properties. So their chemical and physical properties, which you have learned about, would be similar. So something like the how flammable they are would be similar within this family or within this group. So our properties, as I mentioned before, are determined by the electrons in the outer level, those valence electrons. I will use this abbreviation for electron often. For a proton, it will be a P and then a plus sign, and for neutron, it will be an N and then a 0. So when we have electrons that have the same number in the outer shell, they actually means that they're the same. That they're the same group or family. If you look back here, these all have the same number of valence electrons. They all have 2. So an example is like group 1, which is these right here. These are alkali metals. They react explosively with water. If you've ever seen a video of someone throwing sodium into water, it explodes. It's actually really cool. So you can see in our, this is like an abbreviated of our periodic table. This first column are alkali metals. Those all have 1 valence electron. In the second column, which is the alkali earth metals, those all have 2. And then over here we have the boron family, carbon family, nitrogen family, oxygen family, the fluorine family, and then we have our noble gases. They all have the same number within, except right here, which is helium. Helium is happy right there. Basically, the reason that helium is over here is because these are what are called noble gases, which means that they are very happy and they don't like to react with anybody. Helium's the same way, but helium only has 2 electrons, so there's no way for it to have 8 electrons on the outside. And if you'll notice why hydrogen is over here when it should be over here, because it has that 1 valence electron, because it only has 1 electron. Okay, so our periodic table is organized into metals, nonmetals, and metalloids. So you're going to need to know the properties of those. That our metals are good conductors of heat and electricity. So thinking about like copper wires, aluminum, gold is a good conductor. Obviously we wouldn't use that because it's very valuable. They all have luster, which basically means that they're shiny. And these are general rules. Obviously, within every rule in chemistry, there is an exception, so just bear with me. We're going with general rules here. Another thing is that they're malleable, which means we can turn them into different shapes, like taking this lump of coal and making it into a coin, or like those bricks that you usually see when you see gold. or like taking aluminum and making it into either like a shape of a can, or we can make it into foil. Other things that other properties they have is that they are typically ductile, which means that we can stretch them into wires like this copper over here. They're solid at room temperature, except our one little guy here, which is mercury. Mercury is a liquid at room temperature. It is really cool to see in person. Okay, so down here I said left of the zigzag line except hydrogen, which is what I mentioned earlier, that zigzag line right here. So everything to the left of that, everything over here are our metals, except hydrogen up here, who's only over here because of his one valence electron. Okay, so other than metals, we also have our non-metals, which basically think of them as the total opposite. Again, there are exceptions, but for our rules, we are just going to say that they're opposite. They are to the right of the zigzag and including hydrogen. So hydrogen's all by himself over here, but he goes over here to the right. So everything over here is going to be what I'm talking about, except noble gases. Noble gases don't exactly fit. They don't like to react with stuff. So typically nonmetals will lack luster, which means they won't be shiny. They're not going to be good conductors of heat or electricity. We're not going to be able to form them into wires. We are not going to be able to form them into different shapes. Typically, they're found as a solid or a gas, with the exception of bromine, which is a liquid at room temperature, is what this is assuming. So these are two examples of nonmetals. One being carbon. Carbon is it's in pretty much what you're made of. There's a ton of carbon in you, and also you notice that this kind of looks like coal. It's not very shiny. Even though diamonds are also made of carbon and they are shiny, you have to do something to them to be able to make it shiny. So in its natural state, it is not. Also, sulfur over here, notice it's also not shiny. It almost looks like powder, and we're not going to be able to form this into a wire or another shape. It's just kind of there. Okay, so our last one is metalloids, and metalloids are the exceptions to the rule, which, man, you are going to get so sick of hearing that when you take chemistry. There's always an exception. So this has the properties of both of them. So some of them are going to be ductile, some of them are going to be shiny. You can see that right here. We got a couple of them are shiny. Some of them are going to be able to be formed into shapes. Those are found all along the zigzag line. So these are all of our examples, all of our metalloids, and then I added polonium over here because he wasn't on that picture. Our zigzag line right here, you can see boron and silicon and arsenic and tellurium and antimony and polonium. They're all over here, so those are our zigzags. Obviously not every single one of these is a metalloid because aluminum is not a metalloid. It is a metal. Okay, so I have one slide left, which is going over reactivity. So the big thing about this periodic table is how fantastic it is at, you can read it. You can look at it, and you know things about them just by looking at it. You know that these guys are related in some way. You know that these are all related in some way, that they have like a relationship or something that's similar between them. Like these guys are always going to want to react with these guys, which is why you see sodium chloride, lithium fluoride, sodium bromide. All of those are, this first column, this first group really likes to react with this number 17. And this is the fluorine group. These are actually our halogens. So they always want to react with those. So one of the things that I want you to be able to recognize is reactivity. So if you look at the metal activity, so the blue ones up here, as you go to the left and as you go down, they become more reactive. So as you go down this list, they become more reactive. So cesium right here is more reactive than sodium up here. And if you look here, like magnesium is more reactive than aluminum since it increases as you go to the left. For nonmetals, just think of it, as long as you know one of them, you'll be able to figure out the other one. That is the opposite. It increases as you go up. So krypton here is more reactive than neon, which these are bad examples because they're noble gases, but bromine is more reactive than fluorine. And it also increases as you go this way. Oh, wait, I said that wrong. Fluorine is more reactive than bromine. Fluorine is like super reactive. It likes everything. So as you go to the right and as you come up, it is more reactive. So think of fluorine as being the most reactive. So oxygen would be less reactive than fluorine.